In this video, we will see about single phase full bridge inverter. What is an inverter? So, inverter is a circuit which converts DC to AC at desired voltage magnitude and frequency. Let us see some of the applications of voltage source inverter. UPS, adjustable speed drives, HVDC system, EV car. There are two different types of voltage source inverter. One is called the single phase inverter and three phase inverter. So in single phase inverter, we have already seen about half bridge inverter in the previous video. So today in this video, we will see about full bridge inverter. Full bridge inverter feeding R load. So this is the circuit. It has 4 thyristors and 4 diodes. A half bridge inverter consists of only one leg, that is 2 thyristor and 2 anti-parallel diode. Full bridge means you have 2 legs. So this is leg 1 and this is leg 2, and load should be connected between the legs. So this is the here thyristors are used. You can use BJT, MOSFET or IGBT, any of the devices. So I am giving the gate current for thyristor 1 and 2 at the same time. So this is thyristor 1 and here it is thyristor 2. So these two devices are turned on at the same instant. So current flows from A to B. So only if T1 and T2 are turned on at the same instant, current can flow through the circuit. So output voltage will be equal to, so this end is connected to A and this end is connected, B is connected to the negative of the supply. So output voltage will be equal to the supply voltage. So V0 equal to Vs when T1 and T2 conducts. When T3 and T4 conducts, so you can see gate pulse is given at this time instant t by 2. So when T3 and T4 starts conduction, current flows from B to A, and the B point of the load is connected to positive Vs and A is connected to negative of the supply. So output voltage is equal to negative of the supply voltage, or it is equal to minus Vs. So in full bridge inverter also you are getting the same square wave output. Only thing is magnitude is plus Vs and minus Vs. You can change this frequency of the square wave output by varying the time period t, or the instant at which devices are turned on can be changed to change the frequency of the output waveform. And since it is considered to be R load, I0 is equal to V0 by R. So in single phase full bridge inverter with R load, the output voltage and current are in phase and diodes are not used. Let us do the Fourier analysis of the output voltage of the inverter. So again it is a square wave with magnitude plus Vs and minus Vs. And in this square wave you have a fundamental component which we want, and we want to know what are the harmonics present in this square wave so that we can eliminate it. So the best thing is to apply Fourier series for this waveform so that we can identify the, or we can separate the fundamental component from the remaining harmonic components. So Fourier series is used to identify what are the harmonics present in this waveform, and we can identify the fundamental component easily. So let us recall the Fourier coefficients which we have already seen in chapter 41. So f of t is equal to this one where a naught, an and bn are called the Fourier coefficients, and this is a constant term, and an and bn formulas are given. Then we have to identify what type of waveform it is. So this waveform, output waveform, is similar to the half bridge inverter except that magnitude alone changes to plus Vs and minus Vs. And we have already seen that this waveform exhibits odd quarter wave symmetry. So only odd harmonics exist and an and a naught terms become 0. So in this case, we have to eliminate a naught and an term because waveform exhibits quarter wave symmetry, odd quarter wave symmetry. So f of t is equal to bn of sine omega t. Now we have to find what is this bn. So f of t is equal to bn, substitute bn formula, and here the limits or these limits are pi and 2 pi. So substitute it, you will get bn is equal to 4 Vs by n pi. So f of t you will get 4 Vs by n pi into sin and omega t. In most of the books directly they might have given this equation. Now let us see the performance parameters of the output voltage waveform. So this is a square wave and this is the fundamental. Sine wave is the fundamental component which we are of interest. So V naught of t is given by this one, which can be, this summation can be written as 4 Vs by n pi where n is equal to 1. So this corresponds to the fundamental component when n is equal to 1. Remaining things are harmonics which we want to eliminate. So if you find the peak value of the fundamental component, so this is of the type Vm sin omega t. So Vm part, that is the peak value, is 4 Vs by pi. So this magnitude is 4 Vs by pi. But the magnitude of the square wave is only Vs, but sine component, the fundamental component magnitude will be greater than the square wave. Then if you find the RMS value, so what is RMS value? Vrms is equal to Vm by root 2. So divided by root 2. So this is the peak value, divide by root 2, you will get the RMS value of the fundamental component. Next we will find the RMS value of the total output voltage. Our output voltage is a square wave. So whenever you have a square wave, if you find the RMS value, you will get only the magnitude of the waveform Vs. So whatever it is the magnitude, you will get always the magnitude of the waveform only as RMS value in case of square wave. And for fundamental component, we have already found. So here 1 represents the fundamental component. So V01 RMS is equal to 2 root 2 Vs by pi, which we have seen earlier. So now we will find the total harmonic distortion. So what for we are finding this total harmonic distortion, it helps to find the total distortion in your output waveform. We want a sinusoidal waveform, but our waveform is a square wave. So we know that our waveform is distorted. So we are going to find how much it is distorted. This is essential because there are IEEE standards which will tell you that only if your waveform has a THT less than say 5%, you can give this to particular equipment. If THT is a higher value and if you give this waveform to a particular equipment, it may damage the equipment. So that is what a IEEE standard will refer to. So we have to find the total harmonic distortion in our output waveform. So THT percentage THT is equal to VRMS, that is the total voltage RMS square divided by fundamental component RMS square minus 1, that is equal to 48.4 percentage. So this is a very high value. So normally we cannot give this type of square wave for high power applications. Let us see the operation of a full bridge inverter connected to a RL load. So when T1 and T2 are conducting, the current flows from A to B. When we stop or when you turn off T1 and T2 and turn on T3, T4, current has to flow from B to A. Since it is a RL load, the current cannot change its direction instantaneously. So T1 and T2 conducts, current flows from A to B. Now we are giving gate pulse for T3 and T4, but our current cannot change its direction immediately, because when T1 and T2 are conducting, current flows from A to B. When T3 and T4 are conducting, current has to flow in opposite direction. But since it is an inductive load, current cannot change its direction immediately. So current has to flow in the same direction A to B. So this diode D3 and D4 conducts in the same direction to carry the current. So once this current becomes 0, T3 and T4 will start conduction. When diodes are conducting, thyristors, the parallel thyristors will be reverse biased by this conduction voltage. So now when T3 and T4 conducting, current flows from B to A. Again when we give gate pulse to T1 and T2, current cannot change its direction. So current has to again flow in this direction B to A. So now diode D1 and D2 will come into action. So this is how diodes play a major role in case of inductive load. Now we will see the voltage waveform. It will be same square waveform plus Vs and minus Vs, but you see the current waveform, it will change. Since it is an inductive load or RL load, current will lag the voltage. So here voltage has started at 0, so current will start later, that is it is lagging. So you check this table, which is already discussed in chapter 40, Introduction to Inverters. You can verify this table, how you are getting this table. Or when T1 and T2 conducts, current will flow from this direction is assumed to be positive, AB. So current is positive. Voltage is also connected to plus Vs and this is connected to negative Vs. So you are getting plus. When D3 and D4 conducts, so D3 is here, D4 is here. So this B will be connected to plus Vs, that is negative of the load is connected to the supply. So you will get minus V, whereas current flows from A to B only, so it is positive. So similarly the table is filled up. Now you can see here voltage is positive, current is negative. So voltage positive, current negative means this fourth case D1 and D2 will conduct. Here voltage positive, current also positive. So T1 and T2 conducts. So here voltage negative, current positive. Voltage negative, current positive means D3, D4 conducts, and both are negative means T3, T4 conducts. So this is how device will conduct. So if it is a L load, you will get this triangular waveform. If it is a RL load, depending upon L and R values, you may get a slightly exponential waveform. Next case, full bridge inverter with RLC load. So it is similar to R load. So if the RLC is over damped, so it will be similar to RL load, except that the shape of the output waveform will be bit sinusoidal. So same thing, D1, D2, T1, T2, D3, D4, T3, T4. The sequence, everything remains same except that waveform appears to be sinusoidal. So in case of underdamped circuit, what happens is that due to the nature of the load is such that the current through the circuit becomes zero by itself. So naturally it will become zero. So that type of circuit is called load commutated circuit. So here if you see, and this circuit, in this case the XC component will be greater than XL component, so the current will be leading the voltage by an angle pi. So this is where the current starts, where voltage will start at 0. So here current will be leading the voltage. This table remains the same, and you can see here, so T1, when both are positive, T1 and T2 contacts, and here voltage is positive, current is negative. Voltage positive, current negative means D1 and D2 will conduct. So similarly you can both are negative, T3, T4 conducts. So here you can see current becomes 0. Here T1 and T2 is conducting, but the current of T1 and T2 becomes 0 before T3 and T4 are turned on. So there is no need of forced commutation circuit for T1 and T2 because it gets turned off due to this nature of the load. Similarly, when T3 and T4 are gated, it will conduct the current and it becomes 0 before T1 and T2 are turned on. So it also gets turned off. That type of commutation is called load commutation. That is due to the presence of RLC components, the current through the load becomes 0 by itself. Now all the waveforms are clubbed together. So you can find that the output voltage waveform remains the same irrespective of the load. So whatever load you connected, voltage waveform remains the same. And in case of R load, both will be in phase. Voltage and current are in phase. In case of L load, it will be a triangular waveform, and in case of RL load, it will be bit exponential waveform, slightly exponential, and if it is overdamped circuit, it will be a sinusoidal waveform. See, in all these three cases, this sequence remains the same. In RLC underdamped circuit, T1 and T2 will conduct first because current is leading the voltage. See, 0 of the current is here, whereas voltage 0 is here. So in these three cases, current will be lagging the voltage. And this table remains the same in all the cases, and you can find that the output voltage doesn't change with respect to load in a voltage source inverter. So the points to remember here are: the inverter converts DC to AC, output voltage is independent of the nature of the load, output current depends upon the load type, inverter output is a square wave, so it is quarter wave symmetry wave, so only hard harmonics exist, and the magnitude of the fundamental component is greater than the magnitude of the inverter output voltage, and THT is independent of the output voltage magnitude. And if you need the material for this one, you can visit this website. And if you like the content, subscribe to Read Electric Vehicle channel. These are the references I have used.